Another question you might have is that how can we actually improve the performance of single models? When we have ensembles, we still need to run like 10 models at test time, and that's not so great. And we really want some strategies to improve the performance of our single models. And that's really this idea of regularization, where we add something to our model to prevent it from fitting the training data too well in the attempt to make it perform better on unseen data. And we've seen a couple ideas, a couple methods for regularization already, where we add some explicit extra term to the loss, where we have this one term telling the model to fit the data, and another term that's a regularization term. And you saw this in homework 1, where we used L2 regularization. But kind of, as we talked about in lecture a couple lectures ago, this L2 regularization doesn't really make maybe a lot of sense in the context of neural networks. So sometimes we use other things for neural networks. So one regularization strategy that's super, super common for neural networks is this idea of dropout. So dropout is super simple. Every time we do a forward pass through the network, at every layer, we're going to randomly set some neurons to 0. And every time we do a forward pass, we'll set a different random subset of the neurons to 0. So this kind of proceeds one layer at a time. So we run through one layer, we compute the value of the layer, we randomly set some of them to 0, and then we continue up through the network. So now if you look at this fully connected network on the left versus a dropout version of the same network on the right, you can see that after we do dropout, it kind of looks like a smaller version of the same network where we're only using some subset of the neurons. And this subset that we use varies at each iteration, at each forward pass. So the question is, what are we setting to 0? It's the activations. So each layer is computing previous activation times a weight matrix gives you your next activation. And then you just take that activation, set some of them to 0, and then your next layer will be like partially zeroed activations times another matrix gives you your next activation. Question is, which layers do you do this on? So it's more common in fully connected layers, but you sometimes see this in convolutional layers as well. When you're working in convolutional layers, sometimes instead of dropping each activation randomly, instead you sometimes might drop entire feature maps randomly. So so you have in convolutions you have this channel dimension, and you might drop out entire channels rather than random elements. So dropout is kind of super simple in practice. It only requires adding like 2 lines, like 1 line per dropout call. So here we have like a 3-layer neural network, and we've added dropout, and you can see that all we needed to do was add this extra line where we randomly set some things to 0. So this is super easy to implement. But the question is, why is this even a good idea? Like we're like seriously messing with the network at training time by setting a bunch of its values to 0. And like, how can this possibly make sense? So one sort of slightly hand-wavy idea that people have is that dropout helps prevent co-adaptation of features. So maybe if you imagine that we're trying to classify cats, maybe in some universe the network might learn like 1 neuron for having an ear, 1 neuron for having a tail, 1 neuron for the input being furry, and then it kind of combines these things together to decide whether or not it's a cat. But now if we have dropout, then in making the final decision about catness, the network, it cannot depend too much on any of these 1 features. Instead, it kind of needs to distribute its idea of catness across many different features, and this might prevent overfitting somehow. Another interpretation of dropout that's come out a little bit more recently is that it's kind of like doing model ensembling within a single model, right? Because every time, so if you look at the picture on the left, after you apply dropout to the network, we're kind of computing this subnetwork using some subset of the neurons. And now every different potential dropout mask leads to a different potential subnetwork. And now dropout is kind of learning a whole ensemble of networks all at the same time that all share parameters. And by the way, because of the number of potential dropout masks grows exponentially in the number of neurons, you're never going to sample all of these things. So this is like really a gigantic ensemble of networks that are all being trained simultaneously. But then the question is, like, what happens at test time? So once we move to dropout, we've kind of fundamentally changed the operation of our neural network. So previously, we've had our neural network F be a function of the weights W and the inputs X, but now and then produce the output Y. But now our network is also taking this additional input Z, which is some like random dropout mask, and that Z is random. And having randomness at test time is maybe bad. Like imagine that you're working at Facebook and you want to like classify the images that people are uploading, and then like today your image gets classified as a cat and tomorrow it doesn't. Like that would be really weird and really bad. So you'd probably want to eliminate this stochasticity at test time once the network is already trained. So then we kind of want to average out this randomness. And if you kind of write this out, you can imagine actually like marginalizing out this randomness with some integral. But in practice, this integral is like totally intractable. We don't know how to evaluate this thing. Like, you're in bad shape. One thing you might imagine doing is approximating this integral via sampling, where you kind of draw multiple samples of z and then average them out at test time. But this still would introduce some randomness, which is a little bit bad. Thankfully, in the case of dropout, we can actually approximate this integral in kind of a cheap way locally. So if we consider a single neuron, the output is A, the inputs are x and y with two weights, w1, w2. Then at test time, our value A is just w1x plus w2y. But now imagine that we trained this network. During training, we used dropout with probability 1/2 of dropping our neurons. And now the expected value of A during training, we can kind of compute analytically for this small case. It's just one, because there's 4 possible dropout masks, and we're going to average out the values across these 4 masks. And we can see that the expected value of A during training is 1/2 w1x plus w2y. So there's this disconnect between the average value, this average value of w1x plus w2y at test time, and at training time, the average value is only half as much. So one cheap thing we can do is that at test time, we don't have any stochasticity. Instead, we just multiply this output by the dropout probability. And now these expected values are the same. So this is kind of like a local, cheap approximation to this complex integral. And this is what people really commonly do in practice with dropout. Right, so at dropout, we have this predict function, and we just multiply our outputs of the layer by the dropout probability. So the summary of dropout is that it's like really simple. On the forward pass, you're just adding like 2 lines to your implementation to randomly zero out some nodes. And then at the test time prediction function, you just added one little multiplication by your probability. So dropout is super simple. It tends to work well sometimes for regularizing neural networks. By the way, one common trick you see sometimes is this idea of inverted dropout. So maybe at test time, you care more about efficiency, so you want to eliminate that extra multiplication by p at test time. So then what you can do is, at test time, you use the entire weight matrix, but now at training time, instead you divide by p, right? Because training is probably happening on a GPU. You don't really care if you do 1 extra multiplied at training time, but then at test time, you kind of want this thing to be as efficient as possible. Yeah, so the question is, what happens to the gradient during training with dropout? So then you're right, we only end up propagating the gradients through the nodes that were not dropped. And this has the kind of the consequence that when you're training with dropout, typically training takes longer, because at each step, you're only updating some subparts of the network. So when you're using dropout, it typically takes longer to train, but you might have a better generalization after it's converged. And dropout we kind of saw is like this one concrete instantiation of this a little bit more general strategy for regularization, where during training, we add some kind of randomness to the network to prevent it from fitting the training data too well, to kind of mess it up and prevent it from fitting the training data perfectly. And now at test time, we want to average out all that randomness to hopefully improve our generalization. So dropout is probably the most common example of this type of strategy. But actually, batch normalization kind of fits this idea as well. So remember, in batch normalization, during training, one data point might appear in different mini batches with different other data points. So there's a bit of stochasticity with respect to a single data point with how exactly that point gets normalized during training. But now at test time, we kind of average out this stochasticity by using some global estimates to normalize rather than the per mini batch estimates. So actually, batch normalization tends to have kind of a similar regularizing effect as dropout, because they both introduce some kind of stochasticity or noise at training time, but then average it out at test time. So actually, networks, when you train networks with batch normalization, sometimes you don't use dropout at all, and just the batch normalization adds enough of a regularizing effect to your network. But dropout is somewhat nice because you can actually tune the regularization strength by varying that parameter p, and there's no such control in batch normalization. So another kind of strategy that fits in this paradigm is this idea of data augmentation. So during training, in a vanilla version for training, we have our data, we have our label, we use it to update our training, our CNN at each time step. But instead, what we can do is randomly transform the image in some way during training such that the label is preserved. And now we train on these like random transformations of the image rather than the original images. So sometimes you might see random horizontal flips, because if you take a cat and flip it horizontally, it's still a cat. sometimes you'll see you'll randomly sample crops of different sizes from the image because the random crop of the cat is still a cat. And now, then during testing, you kind of average out this stochasticity by evaluating with some fixed set of crops, often the four corners and the middle and their flips. So what's very common is that when you read, for example, papers on ImageNet, they'll report a single crop performance of their model, which is just like the whole image, and a 10 crop performance of their model, which are these these 5 standard crops plus their flips. Also with data augmentation, you'll sometimes use color jittering, where you might randomly vary the contrast or brightness of your image during training. And you can get a little bit more complex with color jittering as well, where you try to make color jitters that are maybe in the PCA directions of your data space or whatever, where you kind of like do some color jittering in some data-dependent way. But that's a little bit less common. But in general, data augmentation is this like really general thing that you can apply to just about any problem, where like whatever problem you're trying to solve, you kind of think about like what are the ways that I can transform my data without changing the label. And now during training, you just apply these random transformations to your input data, and this sort of has a regularizing effect on the network because you're again adding some kind of stochasticity during training and then marginalizing it out at test time. So now we've seen kind of 3 examples of this pattern: dropout, batch normalization, data augmentation. But there's many other examples as well. And once you kind of have this pattern in your mind, you'll kind of recognize this thing as you read other papers sometimes. So there's another kind of related idea to dropout called drop connect. So with drop connect, it's the same idea, but rather than zeroing out the activations at every forward pass, instead we randomly zero out some of the values of the weight matrix instead. But again, it kind of has this similar flavor. Another kind of cool idea that I like, this one's not so commonly used, but I just think it's a really cool idea, is this idea of fractional max pooling. So normally when you do like 2x2 max pooling, you have these fixed 2x2 pooling regions over which you pool over in the forward pass. But now with fractional max pooling, every time we have our pooling layer, we're going to randomize exactly the regions over which we pool. So here in the example on the right, I've shown like 3 different sets of random pooling regions that you might see during training. And now during test time, you kind of average the stochasticity out by trying many different, by either like sticking to some fixed set of pooling regions or drawing many samples and averaging over them. So that's kind of a cool idea, even though it's not so commonly used. And another really kind of surprising paper in this paradigm that actually came out in the last year, so this is new since the last time we talked to class, is this idea of stochastic depth. So here we have a network on the left. So the idea is that we have a very deep network, and we're going to randomly drop layers from the network during training. So during training, we're going to like eliminate some layers and only use some subset of the layers during training. And now during test time, we'll use the whole network. So this is like kind of crazy. It's kind of amazing that this works. But this tends to have kind of a similar regularizing effect as dropout and these other strategies. But again, this is like super like cutting edge research. So this is not super commonly used in practice, but it is a cool idea. Oh, so the question is, do you usually use more than one regularization method? So it kind of like you should generally be using batch normalization as kind of a good thing to have in most networks nowadays because it helps you converge, especially for very deep things. So in many cases, batch normalization alone tends to be enough. But then sometimes if batch normalization alone is not enough, then you can consider adding dropout or other things once you see your network overfitting. So you generally don't do kind of a blind cross-validation over these things. Instead, you kind of add them in a targeted way once you see your network is overfitting. So one quick thing is this idea of transfer learning. So we've kind of seen with regularization, we can help reduce the gap between train and test error by adding these different regularization strategies. And another way that you can, so one problem with overfitting is sometimes you overfit because you don't have enough data. You want to use a big, powerful model, but that big, powerful model just is going to overfit too much on your small data set. So regularization is one way to combat that, but another way is through using transfer learning. So transfer learning kind of busts this myth that you don't maybe need a huge amount of data in order to train a CNN. So the idea is really simple. So you'll maybe first take some CNN. Here is kind of a BGG style architecture. You'll take your CNN, you'll train it in a very large data set like ImageNet, where you actually have enough data to train the whole network. And now the idea is that you want to apply the features from this data set to some small data set that you care about. So maybe instead of classifying the 1,000 ImageNet categories, now you want to classify like 10 dog breeds or something like that. And you only have a small data set. So here, our small data set only has C classes. So then what you'll typically do is, for this last fully connected layer that is going from the last layer features to the final class scores, this now you need to reinitialize that matrix randomly. In this case, going from, because for ImageNet it was a 4096 by 1000 dimensional matrix, and now for your new classes, it might be 4096 by C or by 10 or whatever. So you reinitialize this last matrix randomly, freeze the weights of all the previous layers, and now just basically train a linear classifier and only train the parameters of this last layer and let it converge on your data. And this tends to work pretty well. This tends to work pretty well if you only have a very small data set to work with. And now, if you have a little bit more data, another thing you can try is actually fine-tuning the whole network. So after that top layer converges, and after you learn that last layer for your data, then you can consider actually trying to update the whole network as well. And if you have more data, then you might consider updating larger parts of the network. So a general strategy here is that when you're updating the network, you want to drop the learning rate from its initial learning rate, because probably the original parameters in this network that converged on ImageNet probably work pretty well generally, and you just want to change them a very small amount to tune performance for your data set. So then when you're working with transfer learning, you kind of imagine this kind of 2x2 grid of scenarios where on the one side you have maybe very small amount of data for your data set or very large amount of data for your data set. And then maybe your data is very similar to images. Like ImageNet has a lot of pictures of like animals and plants and stuff like that. And if you want to just classify other types of animals and plants and other types of images like that, then you're in pretty good shape. Then generally what you do is if your data is very similar to something like ImageNet, then you can, if you have a very small amount of data, you can just like basically train a linear classifier on top of features extracted using an ImageNet model. And if you have a little bit more data to work with, then you might imagine fine-tuning your data. However, you sometimes get in trouble if your data looks very different from ImageNet. Like maybe if you're working with like maybe medical images that are like X-rays or CAT scans or something that looks very different from images in ImageNet. In that case, you maybe need to get a little bit more creative. Sometimes it still works well here, but you might need, those last layer features might not be so informative. You might consider like reinitializing larger parts of the network and getting a little bit more creative and trying more experiments here. And this is somewhat mitigated if you have a large amount of data in your very different data set, because then you can actually fine-tune larger parts of the network. So another point I'd like to make is this idea of transfer learning is super pervasive. It's actually the norm rather than the exception. So as you read computer vision papers, you'll often see system diagrams like this for different tasks. So on the left, we're working with object detection. On the right, we're working with image captioning. And both of these models have a CNN that's kind of processing the image. And in almost all applications of computer vision these days, most people are not training these things from scratch. Almost always that CNN will be pre-trained on ImageNet and then potentially fine-tuned for the task at hand. Also, in the captioning sense, sometimes you can actually pre-train some word vectors relating to the language as well. So you maybe pre-train the CNN on ImageNet, pre-train some word vectors on a large text corpus, and then fine-tune the whole thing for your data set. Although in the case of captioning, I think this pre-training with word vectors tends to be a little bit less common and a little bit less critical. So the takeaway for your projects and more generally as you work on different models is that whenever you have some large data set or whenever you have some problem that you want to tackle, but you don't have a large data set, then what you should generally do is download some pre-trained model that's relatively close to the task you care about, and then either reinitialize parts of that model or fine-tune that model for your data. And that tends to work pretty well, even if you have only a modest amount of training data to work with. And because this is such a common strategy, all of the different deep learning software packages out there provide a model zoo where you could just download pre-trained versions of various models. So in summary today, we talked about optimization, which is about how to improve the training loss. We talked about regularization, which is improving your performance on the test data. Model ensembling kind of fit into there. We also talked about transfer learning, which is how you can actually do better with less data. So these are all super useful strategies. You should use them in your projects and beyond. And next time, we'll talk more concretely about some of the different deep learning software packages out there.
지난 시간에는 여러 개의 모델을 사용해서 퍼포먼스를 개선하는 앙상블에 대해서 알아봤는데, 이번 시간에는 싱글 모델로 퍼포먼스를 개선하는 레귤러라이제이션에 대해서 알아보도록 하겠습니다. 레귤러라이제이션의 기본 아이디어는 람다 RW와 같은 모델의 컴플렉시티를 반영하는 term을 로스를 계산하는데 포함하는 것입니다. 이전에 L2 레귤러라이제이션에 대해서 학습한 적이 있는데, 뉴럴 네트워크에서 사용되는 다른 레귤러라이제이션에 대해서 알아보도록 하겠습니다. 많이 사용되는 레귤러라이제이션으로 드롭아웃이 있습니다. 포워드 패스에서 뉴런의 값을 랜덤하게 0으로 세팅합니다. 드로핑하는 확률은 하이퍼 파라미터인데 0.5가 흔히 사용됩니다. 왼쪽 그림은 원래의 뉴럴 네트워크이고, 오른쪽 그림은 5개가 랜덤하게 드롭아웃된 뉴럴 네트워크입니다. 오른쪽은 드롭아웃을 사용한 3레이어 네트워크의 포워드 패스이고, 오른쪽은 트레인 스텝의 코딩을 나타내고 있습니다. 드롭아웃이 좋은 아이디어가 될 수 있는 가능성에 대해서 보겠습니다. 드롭아웃의 동작 메커니즘은 특정 피처에 지나치게 어댑트하는 것을 프리벤트하는 것입니다. 또 다른 인터프리테이션은 드롭아웃이 거대한 모델의 앙상블을 트레이닝하는 효과를 가져온다는 것입니다. 드롭아웃은 우리의 아웃풋을 랜덤하게 만듭니다. 이전에는 아웃풋 레이블 y가 인풋 이미지 x의 함수였다면, 드롭아웃에서는 인풋에 랜덤 매스크 z가 추가된 것과 같습니다. 따라서 우리는 테스트 타임에서 랜덤니스 값을 평균을 취하는 것을 원할 수 있습니다. 그러나 이러한 인테그럴 값을 구하는 것은 쉬운 문제가 아닙니다. 따라서 인테그럴의 근사값을 구하도록 합니다. 먼저 싱글 뉴런의 사례를 보겠습니다. 테스트 타임에서 a의 기대값은 w1x 더하기 w2y입니다. 각각의 뉴런이 제로가 될 확률이 2분의 1이라고 하면, 네가지 경우의 수가 생겨서 확률 4분의 1씩을 곱해주면 a의 기대값은 2분의 1 곱하기 w1x 더하기 w2y가 됩니다. 이렇게 트레이닝 타임과 테스트 타임에서 값이 차이가 나는 경우, 쉽게 해결하는 방법은 테스트 타임에서 그만큼의 확률을 곱해주는 것입니다. 정리하면 테스트 타임에서 모든 뉴런들이 액티브하기 때문에 우리는 각각의 뉴런에 대해서 액티베이션을 스케일해서 테스트 타임에서 아웃풋이 트레이닝 타임에서의 아웃풋 기대값과 같도록 합니다. 드롭아웃에 대한 서머리입니다. 포워드 패스에서 트레이닝을 할 때에는 드롭을 하고, 테스트 타임에서는 스케일을 하도록 합니다. 인버티드 드롭아웃은 드롭아웃을 약간 변형시킨 것인데, 테스트 타임에서 확률을 곱해주지 않기 위해서 트레이닝 타임에서 대신 확률 값을 나눠준 것입니다. 그 이유는 트레이닝 타임이 길어지더라도 테스트 타임이 빠른 것을 선호하기 때문입니다. 레귤러라이제이션에서 드롭아웃을 좀 더 일반화시키면 트레이닝 단계에선 어떤 랜덤니스를 더하는 것이고, 테스팅 타임에서는 그런 랜덤니스를 에버리지 아웃 하는 것입니다. 어떤 경우에는 approximate 합니다. 예를 들어서 배치 노멀라이제이션 경우에 트레이닝 단계에서 랜덤 미니 배치의 스탯을 통해서 노멀라이즈를 합니다. 테스팅에서는 픽스드 스탯으로 노멀라이즈 합니다. 이러한 패러다임에 속하는 또 다른 레귤러라이제이션으로 데이터 오그멘테이션이 있습니다. 바닐라 버전에서는 이미지와 레이블을 로딩해서 CNN을 통해서 훈련시킬 수 있습니다. 또 다른 방법은 트레이닝 동안에 인풋을 랜덤하게 트랜스폼할 수도 있습니다. 이 경우에 오리지널 이미지로 트레이닝을 시킨 것이 아니라 랜덤하게 트랜스폼된 이미지로 트레이닝을 시킨 것입니다. 트랜스폼에는 여러 종류가 있는데, 호리존털 클립은 수평으로 이미지를 클립하는 것입니다. 트레이닝 단계에서 랜덤 크롭과 스케일로 샘플할 수도 있습니다. 오른쪽 그림의 붉은 박스는 랜덤 크롭과 스케일의 사례를 보여줍니다. 컬러 지터를 할 수도 있습니다. 컨트라스트와 브라이트니스를 랜더마이즈 할 수 있습니다. 데이터 오그멘테이션에서는 여러분들이 크리에이티브해질 수 있습니다. 트랜슬레이션, 로테이션, 스트레칭, shearing, 렌즈 디스토션 등 여러 가지를 혼합해서 할 수도 있습니다. 레귤러라이제이션을 정리하면 다음과 같습니다. 트레이닝에서는 어떤 랜덤한 노이즈를 더합니다. 테스팅에서는 노이즈를 marginalize, 소외시키도록 합니다. 가장 쉬운 방법으로 평균값을 구하는 것이 있습니다. 그 사례로는 dropout, batch normalization, data augmentation 등이 있습니다. 이 외에도 drop connect, fractional max pooling, stochastic depth 등이 있습니다. 다음은 transfer learning입니다. 학습을 전이하는 것입니다. CNN은 트레인하고 사용하는데 많은 데이터를 필요로 합니다. 트랜스퍼 러닝은 이러한 믿음을 깨고 적은 데이터로도 트레이닝하고 사용할 수 있도록 하는 것입니다. CNN으로 트랜스퍼 러닝하는 것에 대해서 알아보겠습니다. 첫 단계로 이미지넷과 같은 라지 데이터셋으로 트레이닝을 수행합니다. 두 번째 단계로 스몰 데이터셋을 가진 C계 클래스에 대해서 맨 마지막 단만 리이니셜라이제이션을 하고 트레인을 합니다. 나머지 레이어에 대해서는 프리즈를 합니다. 세 번째로 비거 데이터셋에 대해서는 마지막에 fully connect된 3개 레이어를 트레인합니다. 나머지 레이어들은 프리즈합니다. 이러한 방식은 이미지넷을 통해서 트레인된 파라미터들이 일반적으로 잘 동작하고 여러분의 데이터를 위해서 파인 튜닝만 필요할 때 적합합니다. 트랜스퍼 러닝을 하는데 여러분이 very little data인 경우도 있고 quite a lot of data인 경우도 있습니다. 이때 very similar 데이터셋이면 어떤 경우에든 좋은 결과를 낼 수 있습니다. 데이터 양이 작으면 톱 레이어에 리니어 클래시파이어를 사용합니다. 데이터 양이 많으면 몇 개의 레이어를 파인 튜닝합니다. 데이터셋이 크게 다를 경우 더구나 가지고 있는 데이터가 작을 경우에 문제가 발생합니다. 톱 레이어가 아니라 다른 스테이지에서 리니어 클래시파이어를 사용해 볼 수 있지만 문제가 해결되지 않을 수도 있습니다. 만일 여러분이 많은 데이터를 가지고 있으면 많은 레이어에 대해서 파인 튜닝을 시도해 봅니다. CNN을 이용해서 트랜스퍼 러닝을 하는 것은 많이 퍼져나가고 있습니다. 예외적인 현상이 아니라 표준이 되어가고 있습니다. 여러분들이 논문을 읽게 되면 서로 다른 태스크들에 대해서 이러한 시스템 다이어그램들을 보게 됩니다. 왼쪽은 CNN을 트랜스퍼 러닝해서 오브젝트 디텍션을 하는 것입니다. 오른쪽은 CNN에 RNN을 더해서 이미지 캡셔닝을 하는 것입니다. 붉은 박스는 CNN이 이미지넷으로 프리트레인 된 것을 표시한 것입니다. 이미지 캡셔닝에서 녹색 박스는 월드 벡터가 월드2 백으로 프리트레인 된 것입니다. 다음은 여러분의 프로젝트를 위해서 기억해야 될 요점입니다. 여러분이 관심을 가진 데이터셋이 100만 개 이미지 이하라고 가정하겠습니다. 첫째로 여러분과 유사한 데이터를 가진 very large 데이터셋을 찾아서 컴포넌트를 트레인합니다. 두 번째로 여러분의 데이터셋을 트랜스퍼 런하도록 합니다. 아래에는 프리트레인된 모델에 대한 주소가 있으니 참고하시기 바랍니다. 서머리입니다. 옵티마이제이션에서 모멘텀, RMS 프롭, 아담 등을 배웠습니다. 레귤러라이제이션은 드롭아웃 등을 배웠습니다. 트랜스퍼 러닝에서 배운 것들을 여러분의 프로젝트에서 사용하시기 바랍니다.